Back in episode 41, we talked about the time balance product of the field and the number of temporal modes in the field as a motivation for the use of coherence functions. The problem that we discussed was that the photon number per mode is much less than 1, so the actual electrical field in the modes is not measurable. So that's why we're talking about coherence functions. But we haven't talked about coherence functions as represented on modes. Now, if you go back to chapter 2, many lectures ago, when we talked about modes as descriptors of fields and as a mechanism for us to describe continuous fields with discrete values, you kind of recall this concept of a mode. Mode, in the sense we're going to use it here, is a solution to the Maxwell equations that satisfies boundary conditions. And we describe systems in terms of orthogonal modes so that we can have a variety of modes in the system represented here by, let's say, inputs to these fibers. But each mode is an orthogonal distribution, so we can represent the field as its state on each of the modes. And then in optical systems, we transform modes spatially. If it's a reversible system, the number of modes will stay the same and the modes will remain orthogonal, but we can implement some transformation that you can think of as in the end, a vector matrix multiplication of transforming a set of input modes to a set of output modes, which are superpositions of the input modes. So it's like basis functions changing from one basis to another. This figure is from this paper by David Miller, where he talks about universal linear components, something that can transform any set of modes into any other set of modes. Here, we're going to be more interested in just a very simple device that can abstract a mode. So once we've defined a mode, we're going to assume that we could measure the field on that mode. And we're going to now describe coherence functions as represented on modes, which allows us to take what we've described so far as continuous coherence distributions and turn them into discrete matrix representations. Let's get into it. Computational imaging. Episode 46, Coherent Modes. Here again is this concept of a mode. So we have a fiber coming in. The fiber is a step-walled fiber, so it has these different spatial distributions that satisfy the boundary conditions at the edge of the fiber and are propagating modes, and they create different spatial patterns. In this case, there's a modulator here in the middle that transforms those into different spatial patterns. But since this is a reversible system, these modes will remain orthogonal, and this comes from this lighttrans.com website. So we want to use these modes to describe coherence. Going back to episode 41, we have these definitions of coherence functions. Today we're going to focus on the mutual intensity as a particularly simple version of a coherence function that doesn't require us to think about spectral or temporal degrees of freedom. We're just interested in the interference of spatial components of the optical field that we'll describe with this mutual intensity. Now, here we've defined these things as representations of expectation values of continuous field distributions. The field, we assume now, is a random variable, so the expectation means average over the ensemble of possible field states. We could instead think of the field as represented on a modal basis, so here we have the field, and we can represent the continuous electric field as a set of amplitudes on a modal basis. The modes themselves are not statistical quantities. They're descriptions of the physical system. And so the statistics come into the interference of the amplitudes of the modes. So we can define the mutual intensity between two modes as the expectation value of their field amplitudes multiplied together as shown here. And then we could represent the continuous mutual intensity as the sum over the modes of these coefficients, Jij, describing the interference or the expectation value of the interference between the amplitudes of those two modes. So this is the same as the continuous distribution of the modal intensity if we substitute the continuous electric field, but now we're able to write the mutual intensity as this matrix of terms describing the interference between two different modes. As an example, let's consider point sources, which was the topic of episode 45. We talked about the mutual intensity created by pairs of point sources. And so we assume that we have a couple of point targets as shown here in the object space, and then in image space, each of those point targets would produce an impulse response. Now, the impulse response, we assume this is a shift invariant imaging system, so the impulse response would be shift invariant, and so the impulse response due to the second point source would be the same as the impulse response to the first point source, but just shifted by some amount, which we'll say is 2 times delta, where delta is this parameter here. So we have a point source at x equals delta and a point source centered at x equals minus delta, and we have the sum of the impulse responses from each of those 2 point sources. So we've expressed this in terms of modes, psi1, which would be the mode corresponding to going through the optical system excited by a point source. These 2 point sources excite the same mode but shifted by the separation in their positions, this 2 delta. And so these are not orthogonal modes, of course, that this is just the same mode shifted. So this expression of J is a correct expression of the mutual intensity created by these 2 point sources, but it's not on a orthogonal modal basis. So we need, if we think of psi1, the field created by an impulse response being one of the modes of the system, we need a second mode that would be orthogonal to that one. A nice one to use would be the derivative of the impulse response. So here we're looking at the sinc, for example, as the impulse response, and this dotted line is the derivative of the sinc. Now the sinc is an even function, so if we assume that the impulse response is even, this phi, the derivative is going to be odd. So as you see here, we have at 0, the derivative is 0 for an even function, and then goes down and it is at maximum at the points where the sinc is 0. So it happens because the sinc is even and its derivative is odd, that the integral of the sinc against its derivative is 0, which means these 2 distributions are orthogonal. So if we appropriately normalize the derivative, we have a pair of orthogonal modes, and we can write the field created by those 2 point sources as a superposition of fields on those 2 modes, where psi1 is the impulse response of the system and psi2 is the spatial derivative of the impulse response. And so here we've written the mutual intensity. So incoherent point sources, here we're assuming that the 2 point sources are creating incoherent fields. The mutual intensity due to 2 incoherent distributions is the sum of the mutual intensities from each of them individually, because they don't have any interference between them. So we have the mutual intensity due to the field at located at x equals delta has this form. Now we had it as psi1 of x minus delta, but we can take x minus delta and assume that that is x. We expand that in a Taylor series in delta. We assume as delta is small, so we've expanded this in a Taylor series using the derivative of the first order mode. So this is the field due to the first point source evaluated at in the coordinate x1, and the field due to that point source in the coordinate x2. This is the mutual intensity due to the first point source. This is the mutual intensity due to the second point source. We rearrange those terms to have now the mutual intensity on the basis of the mode psi1 and the basis of the mode psi2. And so this is an expression of the continuous mutual intensity, but we have these matrix terms. We can write the mutual intensity, as we'll see in just a second, of a matrix of a term 2i on the basis psi1 and 2i times delta over k squared, where k is the normalization factor for the second mode. We don't have cross terms. I mean, the mutual intensity in general will have cross terms of the interference of the field amplitudes between the 2 modes, but in this particular case, because we've assumed that the 2 fields are centered at the origin, that they were evaluating this around the midpoint of the 2 point sources, the cross terms cancel, and we only have terms in the product of psi1 with itself and the product of psi2 with itself. So this is going to allow us to think of the mutual intensity as a matrix. Again, we have J is J11, the interference of the amplitude of the intensity basically in the mode 1,1, but then J12, J13, and so on, and then J21, J22, where each of these terms describes the expectation value of the product of the field drawn from those 2 different mode amplitudes. In this particular case, we only have 2 modes, and the matrix is diagonal. Now, J is a Hermitian matrix. The terms along the off diagonal are, phase conjugated across the diagonal due to the symmetry of either, E I times EJ conjugate or EI conjugate times EJ below the derivative. Now, given J, that's a Hermitian matrix, there is a transformation that would diagonalize it. And so that's a transformation of the modes. If we diagonalize J, we would represent it on a new basis. that basis is called the coherent mode distribution, because for any coherent state, any matrix J describing the coherent state, in general, if we just choose arbitrary modes, the off-diagonal terms will not be zero, and we'll have interference between these modes, but that describes the coherence between these two different modes. And if we diagonalize it, then we're describing the system on modes that have an intensity with themselves and can interfere with themselves, but don't have any expectation value for correlation between themselves. And so that's called the coherent mode decomposition. Let's visualize these modes in the case of our 2 point targets. So we have our 2 point sources, and as we have assumed from the start, each of those point sources would create a impulse response distribution on the output plane. So this would be like the impulse response due to each of those 2 point sources, separated by the 2 delta. But we're not going to represent the field on the impulse which created those 2 point sources. Instead, we want to represent the field on our new modal basis, the psi1 and psi2, corresponding to the impulse response and the and its derivative. So the modes, each of the distributions creates some kind of excitation, which is proportional just to the amplitude of the mode on psi1. This would be psi1. And then we create some other excitation on the mode psi2, which crosses 0 here at the origin and goes to a maximum at the point where the primary mode crosses 0 and then goes back down and oscillates. Now, these modes, these psi1 and psi2, are modes on the output plane and our output plane, but they project similarly onto field distributions on the input plane. So there would be a distribution on the object plane corresponding to psi1, and a distribution. And then this is the so basically when we think about the field that's excited in psi1 of x, the field that is excited in that would be some input distribution f of x overlapping with psi1 of x as represented on the input distribution. Now, as it happens here by design, the derivative mode has a null at the origin. So if there was a point source at the origin, x equals 0 in the object space, that point source creates 0 excitation in psi2 and creates a large excitation in psi1, the primary mode. So this null would create no excitation in psi2, but if we have 2 points that are spread around the origin, those points can't both lie on the null, so we get some excitation in psi2. So what we saw is that the excitation in the secondary mode, the derivative mode, is the square of delta. So as delta goes to 0, we have a single point source. The excitation of the derivative mode is 0. But if delta is not 0, if there's actually 2 point sources, then we have this excitation which goes like the square of delta. Now, the Fisher information relative to delta is again, we have Fisher information relative to the mean position, and here we've assumed that we've already pointed the system at the mean position of the 2 point sources, and then we have the Fisher information, related to the separation. To get the Fisher information, the excitation of psi1 doesn't depend on delta, but the amplitude we would measure in psi2, and again, recall from the introduction, we're assuming that we have a filter that will allow us to pick out that mode psi2 and analyze its amplitude. The amplitude of that is proportional to the separation of those 2 point sources. If we take the derivative of that excitation, that mode amplitude, now we're not measuring a continuous distribution like we did with the RSI, we're just measuring, we have a filter that will pull out that mode and measure its amplitude. If we take the derivative of that measurement with respect to delta, we get something that is linearly proportional to delta. We square that, it's proportional to delta squared. We divide by the original amplitude proportional to delta squared, and we get a Fisher information relative to delta that's independent of delta. So that the cramer bound again doesn't depend on the separation between the 2 point sources. You'll recall that for a conventional imaging system, the Fisher information goes to 0 as delta goes to 0. As the 2 points get closer and closer together, it's no longer possible to tell that they're 2 points. Here, because the Fisher information does not go to 0, even as delta goes to 0, our cramer lower bound for estimating the separation is going to go like the width of the impulse response in this case, divided by the number of photons we collect. So collecting more photons, as we saw in episode 45, will allow us to overcome the Rayleigh criteria and estimate the separation even as the separation goes to zero. This idea that the Fisher information doesn't depend on separation is the same situation we saw. This is a slide from episode 45 showing the Fisher information for a rotational shear interferometer measuring the separation between 2-point sources. And this is the separation delta between the 2-point sources. And even as it goes to zero, this was the sum of the Fisher information of the two arms of the RSI. For the case of this mode measurement system, we only have to measure the amplitude of the second mode, and its Fisher information with respect to the separation stays constant. This strategy of projecting the field onto a modal basis in the measurement as opposed to using an interferometer is called mode sorting. Here's an example paper discussed in the text about a mode sorting filter that is useful for measuring a exoplanet to isolate the exoplanet's signal from the signal due to a star by, in this case, having a set of diffractive elements that isolate each of a set of modes and then occluding the fundamental mode and measuring the amplitude of the secondary modes on a detector. And by this mechanism, you can super resolve exoplanets. So a very interesting, very cool thing to really understand this in more detail. It will be helpful for us to understand focal systems with the coherence analysis, which is the topic of Chapter 8 that we'll get into right after we get into the next episode, which is going to use the coherent mode concept to build on a topic that we talked about in Chapter 6, back in Chapter 5, I think, where we talked about imaging through inhomogeneity by characterizing the homogeneity and its amplitude on the coherent field. We can do that as well with incoherent field distributions by measuring the impact of the inhomogeneity on the coherent modes. So in our next episode, we'll talk about use of an RSI to measure the coherent modes of a system and then compensate for the distortion of the turbulence in the path of the system to image through turbulence using coherent modes. All right, so I'll see you in episode 47.